Hi, my name is Tristan de Condé, and I'm a product marketing engineer in the temperature and humidity sensing division at Texas Instruments. Today, we will talk about how to achieve thermal safety in automotive infotainment and cluster applications. So why is this important? Well, new cars are increasingly getting equipped with more features, from connectivity to internet, your phone, medias, safety features, and more. Furthermore, there are more and more displays in the car that are becoming larger in size with higher resolution. To cope with the complexity of these systems, it's becoming common to see the centralization of functions under one system. And finally, customers have higher expectations for the human-machine interface and the way they interact with the car. It has to be quick, easy to use, and with a quality experience. All in all, these criteria are leading to cars with more embedded processing power, which in turn consumes a lot more energy and dissipates a lot more heat. Since infotainment systems are critical to the driving experience, car manufacturers need to protect passengers by mitigating any risk of over-temperature damage, as well as making sure that their system runs safely at maximum performance in any situation. So now, let's dig into how. So when we talk about helping car manufacturers solve their infotainment and clusters thermal challenges, we'll focus on typical issues that design engineers are confronted in three different end equipments. First, we'll dig into the main brain of the car, the head unit. Because it features big, high-performance microprocessors, most of the heat generation comes from the core itself. So we'll see how to reliably monitor the temperature directly from the microprocessor's die thanks to our low-power remote temperature sensor, the TMP451Q1. Secondly, we'll discuss how the reconfigurable cluster will benefit from closed system temperature monitoring in order to push the MCU's performance closer to the edge, operating at its optimal temperature range. To achieve this, we'll introduce our accurate analog temperature sensor, the TMP235Q1. Finally, we'll review how the USB chargers can heat up dramatically and how they can be easily protected from over-temperature damage thanks to a simple threshold detection using our latest temperature switch, the TMP390Q1. Alternatively, for all these end applications when basic requirements are to be met, our cost-effective thermistor can also be used. The TMP61Q1 is a silicon-based linear thermistor with a positive thermal coefficient. It's a new addition to our portfolio and is great to replace NTCs as it has a better accuracy and sensitivity in comparison, especially at high temperature. Let's start with the main control panel for the infotainment system, the head unit. It aggregates many different functions that were formerly dispersed in the car with various push buttons. Here you can see a block diagram depicting the vehicle interface processor and the main components surrounding it. You can see the temperature sensor communicates with the MCU in I2C while remotely sensing the temperature at the core of the processor via a PN junction on the die, which has a very predictable transfer function. This is how we derive the temperature after pushing different currents through the collector and measuring the delta VBE voltage. So now, what are we doing with these temperature measurements? Typically, alert functions are used as interrupts to modify the system behavior when the temperature gets above a critical threshold. As you can see in this graph, with two alert functions, therm and therm2, the thermal management of the system can be more granular. The first threshold acts as a warning to activate a cooling system, and the second one to shut down the system to avoid thermal damage. The TMP451Q1 is our newest remote temperature sensor designed for this use case with a plus or minus 1 degree Celsius typical accuracy from minus 40 to 125 degrees Celsius, whether for the remote channel or locally. So it can give two readings, one at the core of the microprocessor and one where the temperature sensor is placed on the board, giving an indication of the ambient temperature as well as temperature inside the microprocessor. Now let's focus on the instrument cluster behind the steering wheel that is now fully digital and completely reconfigurable. These are critical systems in the car that give crucial information to the driver like speed, gauge level, RPM, direction, etc. Similar to the head unit, clusters have demanding processing requirements and heat up quickly. particularly because ventilation is usually non-existent in these systems due to the very little space available. So very small temperature sensors are placed as close as possible to the processor in order to get relevant sensor data. In comparison with thermistors that require a voltage divider and other linearizing support circuitry, the small overall system footprint of analog temperature sensors are advantageous here. As there is no room for error in such a critical system, there needs to be high temperature accuracy to ensure passenger safety. Thanks to the accuracy of these temperature readings, design engineers can push the performance of the system closer to its thermal design limits, or reduce system costs by choosing a microprocessor with lower specifications. For example, most processors have built-in temperature sensors, which, due to variations across wafers, have an accuracy of about plus or minus 4 degrees Celsius. If we have an external temperature sensor with plus or minus 1 degree Celsius of accuracy, we then have 3 degrees of extra performance room to play with. Our TMP235 has an accuracy of plus or minus 0.5 degrees Celsius. That enables better system performance up to 125 degrees, also called grade 1, or up to 150 degrees Celsius, called grade 0. Finally, let's look at USB chargers. There are multiple ports that can charge phones quickly, such as USB Type-C power delivery. Here, each port delivers 60 watts that can overheat in certain conditions. It's then important to protect passengers against over-temperature damage by detecting when the temperature goes above a certain threshold. In this case, we can simplify the design using a temperature switch, which is a very small IC instead of the usual thermistor. Our TMP390Q1 is a resistor programmable temperature switch that covers a minus 40 to 125 degrees Celsius temperature range with a plus or minus 3 degrees Celsius of accuracy. It's also a low power consumption alternative to the thermistor, as it can be supplied with voltages from 1.62 to 5.5 volts and consumes 0.5 microamp, typically at 25 degrees Celsius. It has two channels that allow for independent overtemperature and undertemperature detection at the same time. It's the simplest thermal protection implementation that can be used when the system needs to be protected from both the cold and the heat. The alerts that it generates can be connected to the USB controller or an MCU to immediately react and save the system from damage. Now that we've seen some use cases where TI temperature sensors can help you design safe and high-performing infotainment systems, let's take a moment to review the full breadth of TI temperature and humidity sensors available to you. Until now, we have only covered onboard temperature sensors like the TMP235, which was an analog temp sensor, the TMP451, which was a remote and digital temp sensor, and the TMP390, which was a temperature switch. But we also have silicon-based PTC thermistors as well as a swath of high-performing digital temp sensors covering most available interfaces from I2C to UART. We also have off-board temperature sensors that only have 2 pins and can go into cables and probes, in addition to a daisy chain connection that allows our sensors to stack themselves to reach up to 300 meters of cabling. Finally, our humidity and temperature sensors can be used in HVAC systems, windshield defoggers, cameras, and more. To learn more about our solutions for infotainment and cluster systems, go to ti.com/temperature, where you'll find other collateral like application notes, reference designs, white papers, and other training videos that have everything you need to know about temperature design challenges. Thanks for watching this video, and until next time, goodbye.